Welcome to Math TV with Professor V. In this video, we're going to talk about continuity and specifically how it relates to and determining the continuity of piecewise defined functions. So just as a little refresher, I want you to think back to our three-part definition for determining if a function is continuous at a number a. Remember, there's three conditions that need to be satisfied. The first is that f of a is defined, meaning that a, that value, is in the domain of f. Second condition is that the limit as x approaches a of f of x exists. And then the third condition basically says that that limit, the result from condition 2, is equal to the function value from condition 1. So these are the three parts of the definition that you need to make sure are satisfied when determining if a function is continuous at some value. However, for the following functions that apply to this theorem, we don't need to check conditions 1, 2, 3. We can just cite the theorem and say the following. So any polynomial is continuous on all real numbers. Any rational function is continuous on its domain. Also, any root, radical function, trig function, inverse trig, logarithmic, exponential, all those functions are continuous on their domains. So if somebody comes up to you, your teacher or someone off the street, who knows, and is like, hey, where is this function continuous? And if you can determine that it's a polynomial, rational, root, trig, etc., if it's one of these guys, then stating where it's continuous is equivalent to stating the function's domain, okay? It obviously gets more tricky when you have a piecewise defined function, and that's what we're going to focus on later, but I want to reinforce this concept first. So we're just going to look at some examples here, let's get rid of that, and determine where the following functions are continuous, okay? So example 1, we have f of x equals 2x squared minus x minus 1 over x squared minus 9. Well, I can tell right off the bat, this is a rational function. So I'm going to cite the theorem. I'm not interested in what number it is, okay? If the theorem doesn't have a name, then don't worry about it. By the theorem, we know that f of x is continuous on its domain. And now let's specifically say what that domain is. So for rational functions, we just have to ensure that the denominator never equals 0. So that means we don't want x squared minus 9 to equal 0. So all x's such that x does not equal plus or minus 3 will be part of the domain for this function. And that's also everywhere that that function is continuous. Okay, next one, we've got g of x equals 2x squared minus x minus 1 over x squared plus 1. Again, this is another rational function. I'm just going to be super thorough and write by the theorem. That means that g of x is continuous on its domain. Well, what's its domain? Let's see. I want to make sure the denominator is not 0. That way g of x is never undefined. But x squared plus 1 can't be 0, right? That would mean x squared has to equal -1, which does not have any real solutions. So that means there's no restrictions on the domain for g of x, which means the domain is all real numbers. So you could write x such that x is any real number. Honestly, I never write it this way. Who likes writing so much? I would just write the domain is all real numbers. Like that. You could write it in interval notation, -infinity to infinity. Okay. Good. So notice I'm not checking conditions 1, 2, and 3 because the theorem applies that these functions all are continuous on their domains. Okay. Q of x equals rad x minus 2. Well, this is a root function or radical function. So again, by our theorem, what is this one called? Q of x is continuous on its domain. What's its domain? Do you remember how to find the domain of a radical function? Well, remember, we can't take even roots. This is an even root because square root, the index is 2. We can't take even roots of negative quantities. So we want to make sure that x minus 2 is greater than or equal to 0, which means x has to be greater than or equal to 2. So that's precisely our domain. The domain is going to be x such that x is greater than or equal to 2. Or alternatively, you could write interval notation 2 to infinity. Okay, last one, which I like. P of x is cube root of x minus 2 over x cubed minus 2. So P of x is a little bit of like a hybrid, right? It's a combo of a root function and a rational function. And the interesting thing here is that since we have an odd index, you're allowed to take cube roots of negative numbers. So there's no restrictions coming from the numerator. The only restrictions that I'm concerned with at this point are the denominator, specifically that x cubed minus 2 does not equal 0. That's what I, don't want to happen. So that means x cubed should not be 2. So x should not be the cube root of 2. Everything else is good to go. Everything else will be in the domain of P of x. So let's see, back to combo of root and rational function. So it's continuous on its domain by the theorem. And what is that domain? Everything except cube root of 2. All real numbers such that x does not equal cube root of 2. So you might be thinking to yourself, my goodness, every single function pretty much is covered under the umbrella of functions that this theorem applies to. Why would I ever check conditions 1, 2, and 3? Because guess what's not here? What's not included are piecewise defined functions. So not included piecewise defined functions. And really the only tricky part about the piecewise defined functions are where they are pasted together, where the domain is chopped up and one function is switched to another function, okay? So let's go through and look at an example now, and you're going to see how we will have to apply our three-part definition for continuity. So f of x is equal to x squared if x is less than -1. It's equal to x if x is between -1 or greater than or equal to -1, strictly less than 1. And f of x is equal to 1 over x if x is greater than or equal to 1. Okay, I'm going to go break it down piece by piece. So if x is less than -1, that's on the interval from -infinity to -1. And on that interval, f of x is equal to x squared, which is a polynomial. So obviously by our theorem, it's continuous on all real numbers. So it will be continuous on the interval from -infinity to -1. I don't need to check anything on that interval. Let's check the next interval. I'm going to write it as an open interval from -1 to 1, because at -1 is where this transition occurs from x squared to x. So we're going to have to investigate that further. But for all other x values that are between -1 and 1, how is f of x defined? It's equal to x, which is again a polynomial. So it's continuous on all real numbers, therefore of course it's continuous on the interval. And then last interval I'm checking, these are all open intervals because I have to investigate what happens specifically at -1 and then again at 1. So just speaking about the open interval from 1 to infinity, f of x is defined to be 1 over x. That's a rational function. It's continuous on its domain. So it's continuous on its domain. Can you tell what its domain is? 1 over x. As long as x isn't 0, we're good to go. But look at the interval, 1 to infinity. That does not include 0. So we are golden. That means 1 over x is continuous, yes, on 1 to infinity. So therefore it's continuous on the interval. So that means all we need to do is investigate. I'm going to write you a little narrative. Look at this. Need to investigate what is going on at x equals -1 and at x equals +1. Because basically we don't know if when this piecewise function, the pieces were pasted together at -1 and 1, if it was done in a continuous fashion or not. But every other x value, we're good. We know the function's continuous there. How fabulous. Okay, let's check. Let's check x equals +1 first. Okay, let's consider x equals 1. You could think of it like a is 1, depending on your book. Okay, so first condition, I have to check that f of 1 is defined. So what is f of 1 equal to? Now be careful. When evaluating into the piecewise defined function, you need to make sure which inequality is inclusive. So f of 1, I'm going to plug it in here because that's for values x greater than or equal to 1. So I'm substituting it into 1 over x. So it's 1 over 1, which is 1. Okay, condition 1 is satisfied. Condition 2, I need to figure out what is the limit as x approaches 1 of f of x. Well, again, since the domain splits here at 1, I have to check the limit from the left and the limit from the right separately. So let's see what's going on. So the limit as x approaches 1 from the left of f of x, that's going to be the limit as x approaches 1 from the left. Which part of the piecewise defined function should we use? So coming from the left of 1 means you're approaching 1 from values smaller than 1. Smaller than 1 is this guy, x. So we're going to replace f of x with x. And then now to find the limit, you just plug in or substitute 1 for x. Now it doesn't matter that it's 1 from the left. Don't do something bizarre like plug in 0.99. I've seen that happen. When you're deciding which part of the piecewise function to use, that's when you look at, okay, is it from the left or from the right? But now that we've already decided, just plug in 1, okay? This is 1. Now let's go from the right. So now we need the limit as x approaches 1 from the right of f of x. Okay, so that's going to be the limit x approaches 1 from the right. F of x is equal to 1 over x if we're coming from the right. Okay. And then now I don't care that I'm coming from the right. I'm just plugging in 1. Okay, so that's 1 over 1, which is 1. Oh, how nice. Okay, so the limit from the left is equal to the limit from the right. So therefore I could say that the two-sided limit exists and it's equal to 1. Great. And then now we're going to check the last condition. Is the function value, is the result from step 1 equal to the result from step 2, the limit? It is. They all equal 1. Yay. So what does this tell us? That f of x is indeed continuous at x equals 1. Great. Okay, so that's taken care of. We still need to investigate what's happening at x equals -1. So why don't you guys pause the video, give that one a try on your own, apply the 3-part definition, and then check back in. Okay, what did you find? Let's do it together. I rewrote the piecewise function here so we wouldn't have to keep scrolling up. So now we're going to consider x equals -1. All right, great. So condition 1, what is f of -1 equal to? Well, when deciding where to substitute it in, I have to look at which inequality is inclusive, right? So it's this one. So f of -1 is just equal to x, so -1. Second condition, we have to figure out what is the limit as x approaches -1 of f of x. And I need to check the limit from the left and from the right. So let's see. The limit as x approaches -1 from the left. So from the left of -1 means we're coming from values smaller than -1. So I'm going to use x squared as my function. So this is the limit x approaches -1 from the left of x squared, and then now I just substitute it in and I get positive 1. From the right, that's the limit, x approaches negative 1 from the right of f of x. So that's the limit, x approaches negative 1 from the right. From the right, f of x is just equal to x. So that's negative 1. Well, in this case, notice the limit from the left is equal to 1, whereas the limit from the right is equal to negative 1. And when they're not equal to each other, that means that the two-sided limit, so just the limit as x approaches negative 1, in general, it does not exist. So since that condition failed, naturally condition 3 is going to fail. I don't even need to state it. You can if you want, but therefore 3 cannot be met. And so that means the function is not continuous at negative 1. So I'll summarize. That means f of x is not continuous at x equals negative 1. But that was the only point of discontinuity. So if the question was asking where is the function continuous, you could just say, therefore, f of x is continuous. How do you say everywhere except negative 1? You could say from negative infinity to negative 1 union negative 1 to infinity. Okay? We can weaken our conditions for continuity and say that this function is continuous from the right of negative 1. And if that idea piques your curiosity, I will link a video right now in this upper right corner where I talk about one-sided continuity, continuity from the left or continuity from the right. Very interesting topic. But anyways, that'll conclude this video. Hope you found it helpful. Subscribe if you haven't already. Give this video a thumbs up. And check out my integral of the day if you're a Calc 2 student. It's quite fun. Also, you can find me on TikTok and Instagram at MathTV with Professor V. All right, stay tuned, guys. See you soon.